for a 1 week break. Hope that wasn't too much of an issue. The way that I've organized the class is that the first 2 weeks we sort of go over a sort of broad topic, a broad concept that we use in astronomy all the time. So this week it's light. The best part is I get to do a demonstration on Thursday about 2 different kinds of light. We'll talk about the first kind today, and then the second kind on Thursday. The first one being essentially the light that comes up everything that has a temperature, basically everything. This is the old, I think it's the old slide, but it is still in the same place, reach.louisville.edu. If you are having issues, and then especially if you're having issues with, I can't review class materials because I don't have a laptop or something like that, this is a good place for general resources. So this is the place to start, the Learning Resource Center. If you are having issues specifically with the physics class, we do have a physics learning center. We call it the PLC. It's in the chemistry building because we're still renovating the physics building. It's the lower level student lounge. I don't know what that is, but that apparently says something to chemists. It's staffed basically from 9 to 2 during the weekday, on Fridays, also to 2 p.m. Tuesdays it's always starts at 10, Wednesdays from 9 to 2, and Thursdays from 9 to 3. So it is available. It has graduate students who know astronomy. There's maybe one astronomy graduate student at least there, and so there's somebody there to help you if you get stuck on the class here. Please use them. They're there. They have to be there. They're paid to be there. Use this resource. Okay, so we talked about what is astronomy, what is science, the fact that I really want to emphasize it's not a belief system. It is really like how we find and figure out what the world is like. So a hypothesis is an idea that we can test, and a theory is a narrative that actually has been proven consistent with observation many times. So I told you Thursday, week before last, always have your voting card ready. Who has a voting card? Who has their voting card with them? Who still needs a voting card? Right. So while I do this, let's see if we can vote. We'll fold it up with the correct answer. I'm too short. Who else? Oh, wow. Yeah, I see hands. Okay, let's see if I've got enough printed. Otherwise, I'll have to ask for more. Colleagues in charge, if you got the first one for free, but after that, you should charge $1. So, beware, bring these things. I think I put the PDF on the website, or on the Blackboard as well, so these I've seen people be clever with their phones, but I like to see these. I got one more person. Oh, how good is this? One exact oh shoot, there's 2 people that are hands up. I'll get to you. I have a few at home, but no longer here. I'm sorry. All right. I had this whole warm, fuzzy feeling like I just have enough of them. All right. Cool. Let's vote on this, right? So, blue and red lights the wavelengths are the same for both. Blue light's shorter than red light is shorter than blue light. At some point, blue light doesn't have a wavelength anymore. What's the correct answer? Oh, you all had it up already. 1, 2, 3. Thank you. You all got that. All right. So blue and red light have the same energy. Red light has more energy than blue. Blue light has more energy than red. That depends on what emits the light. So again, 1, 2, and 3. See everybody's answers. Here we are. So yes, blue light has more energy in it, right? So what's the correct ranking from light energy? Going from Low energy to high energy, so I should have that. Sorry, I'm trying to make mental notes on my slides, but I should fix for next time. Right, voting in one, going from lower energy to higher energy, right? So what goes from the lowest energy to the highest energy? Now voting in one, two, three. All right. See majority, but not uniform. So search your neighbor, even if the two of you agree. Explain to them what your reasoning is, right? So search your neighbor, explain to you why your answer is correct, even if the two of you agree. You've got about 90 seconds. Yes, find an equal. This is it. Three, let's see them again. You convince your neighbor. I'm seeing majority D, so you definitely did a good job. All right, so light has a couple of properties. One, we think of it as a wave, and so that basically it's an oscillation of something. Almost, and I love the fact how much work that word almost is doing. Our knowledge of the universe comes from the direction of light, emitted by distant universe. Basically, in your lifetime, that word has changed. Up until basically when I got to college, we did not have any other information other than the light from the universe. So we've started collecting different things. In vacuum, it always goes at the same speed. Funny enough, in other media, it goes a little slower, but there's, and so it's a constant in vacuum, and we call that C. That's the speed of light. If you remember the one equation, E is mc squared, that's C, that's the speed of light. And so as far as we know, nothing can travel faster than the speed of light. And so that means any information can only go at that speed. So you can only hear about it. And, one part of the universe only knows about the other part of the universe if there was enough time for information to travel from A to B. And so we think of it, we can explain a lot of the information or what we know about light by thinking of it as a wave. And a wave means that there are sort of two crests, and that distance between the two crests here, so the tops of the waves, that's the wavelength. And so our eyes respond to wavelengths with between 350 nanometers, so 10 to the minus 9, and 800 nanometers, 10 to the minus 9. Short wavelengths appear violet, so bluish and almost purple, and longer wavelengths appear red. And so, but you could also think of wavelength, or as if you think about a wave, you can also think about how fast it's going up and down, right? So you can think of that as the frequency. So here's the speed of light, there's the wavelength, and you can convert that into a frequency. And by doing something with math like this, what's always helpful is to think of like what are the units things are in. So the velocity is in meters per second, right? How fast do I go? I travel this many meters per second. The wavelength is in meters. That's our yards of length, or meters of length. So meters per second divided by meters, the only thing I'm left with is 1/2 second. And that's what we do, like we could show it like this. And sometimes the unit we use for that is hertz. This depends on how old your car is, but it might have a radio still, an analog radio in there, like megahertz. You see like the radio stations have when I grew up, there was radio station like 538, it was 538 megahertz, and couldn't see that in the radio that the station was at, right? So you could express the wavelength of light either as a wavelength, or because it's becoming ungainly, or you really come from a different part of science, you've expressed it as a frequency, as hertz. So if you talk to radio astronomers, they'll tell everything in hertz. If you talk to optical astronomers, they say everything in wavelength. I'm sorry, these were two different groups that really didn't talk to each other until well after World War II, so they have their own differences. All right, so if we're talking energy, highest energy, shortest wavelengths, lowest energy, longest wavelength, 10 to the 3, that's a kilometer. So basically these are mile-long wavelengths, right? So you need antennae that are almost a mile across to measure things. Radio waves, microwaves is shorter, so micro, think like centimeters long, or millimeters long. So fractions of an inch there. I could do inches, didn't grow up with them, still confused the hell out of me, but there you go. Infrared and ultraviolet, very close to so on either side of the visible. Infrared is beyond red, ultra is beyond the violet, right? So both of them are sort of, ultra is under violet, I guess, and infrared is beyond red, beyond red and white. But this is only the bit that we're sensitive to with our eyes, and everything else, every time that we built a detector that actually was sensitive to any of the other ones, we sort of opened up a new piece of the universe. Red is the longest wavelength, blue is the shortest wavelength. I love having a GIF, so that way I have a little crutch like long wavelength, yes, that's the one, that's a little red guy that's taking really long steps. That's how I can remember it. I'm skipping that one, it had way too many letters on it, I just realized. This is the crux of the whole week. There are two kinds of ways that you can make light appear. The first one is called thermal radiation, essentially heat it up until it glows. And so you might be familiar with that because if you have an old school light bulb with a filament in it, that actually starts to glow because it heats up, right? I don't know, you might be the LED generation. Who has seen one of these older filament light bulbs and who accidentally touched one? Yeah, you remember that one for sure because it's hot, right? It's hot because you're heating up that filament, and that's what's causing it to glow. Or you could be a little more old school, and this is why the slides from my colleague. He's has a hobby, smithing as a hobby, so he's heated up this eyelet of metal in the forge, and yes, it now glows because it's so hot, right? So that's what we call thermal radiation. And it turns out that's an important thing in nature. But we have a second way to do this, and in fact, I've been pointing with it all for the whole time. Lasers. This is something that we use by an electron transition, and that is done in a very particular color because it's really only one wavelength. This is why laser is only green or only red, right? Your eye perceives it as one color, but in fact it only has one wavelength. And so that electron transitions, that's what we'll talk about, that's what we'll experiment with on Thursday. Okay? So we have two ways to get this, to get light to appear in the universe. And both of them happen naturally, and both of them can be done using technology. The key property for thermal radiation, of course, is that thermal, you're all wearing something thermal, I hope, because it's cold. Thermal is temperature. And so if you have something called a black body, and a black body is a physics thought experiment. There isn't a perfect black body, meaning that there isn't a perfect item in real nature that behaves like that, but a lot of things behave very close to it. And so if you heat it up, it radiates more. If it cools down, it radiates at a lower wavelength. So if you start heating up a piece of metal, for example, it's first red hot, then yellow, then white, and basically it probably melts before it gets to blue. But you may have seen somebody weld something, hopefully from the same distance, and then it's sort of like bluish whitish look. That is the hottest temperature that you can perceive, right? So that's the hot this. And so this is the curve what that looks like. It does emit at all wavelengths. It's not in one particular. And so we measure everything with Kelvin, right? Remember that we're being scientists here, and so we measure everything. It's essentially Celsius that start at absolute zero when no molecules move anymore. So 3,500 Kelvin is definitely not oven temperature. Oven temperature is sort of like 500 Kelvin. And so this is, let's see, 5,000 Kelvin up here. That's the temperature of the surface of the sun. Oh, no coincidence, it's also yellow, which is what, if you briefly looked at the sun, please don't look at the sun for any length of time, it's bad for your eyes. But if you look at it, it's like it has that yellowish color. You go any further, it goes into green and then blue. And so the peak of the wavelength where a typical temperature, the peak temperature, the peak of the wavelength, the peak wavelength where a black body is at depends directly on its temperature. So if I up the temperature, and so then the wavelength goes shorter. So the hotter the thing is, the shorter the wavelength peak temperature is. All right, I got lost in that sentence there for a second. Is everybody okay with what this means? Yeah. Okay. So try to keep it to a minimum. But like we put a concept like this, a black body radiator. It's basically I've taken a lump of something and heating it up, and this is pretty much how it behaves, all the way down to us. So if you see heat signatures of people over night vision, for example, you see people glow, right? Because they have a temperature. And you see more of them in what's uncovered versus what's covered, because you can directly see their temperature, their body temperature, and that body temperature is basically somewhere around 400 Kelvin. So it's over here on this side, which is the infrared, which is where the night camera goes. This is a constant, and so this is Kelvin times meters. It's a very strange unit, right? So it's Kelvin times meters. This is just a constant. So if I have my temperature in Kelvin, I can directly get the peak wavelength in meters, as long as I've got my Wien's constant, right? So this is a constant that we named after it. All right, so what's a good black body? Well, as it turns out, this is one, right? To first approximation, stars radiate like a black body. They radiate with one temperature because the whole thing is sort of in equilibrium, and so it radiates all over with almost the same temperature. If we look at it with the telescope outside the courtyard, for example, we do see some dark spots and some light spots. There are some parts that are a little cooler than the rest, but overall stars behave like black bodies pretty well. This is one of the satellites that's keeping an eye on the sun, and you can see the solar storms we can come at, right? It's a first approximation. Cows are roughly spherical. All right, grab our voting cards. Which one of these two, star A, star B, star A, the same, star C, we can not tell from this graph, which one of these has a longer peak wavelength? Voting 1, voting 2, and voting 3. Which one has a longer peak wavelength? All right, I've got a tile room, this is A. So I will go make a walk around the room, turn to each other, even if the two of you agree, convince them why you're right. Got about 90 seconds. Okay? How are we doing with the curvature? Okay, this side is convinced each other that it's actually C, that side is pretty much convinced it's A, and I'm realizing something. I'm showing a graph on a round surface. So for you, it looks a little off. For you, it looks a little off the other way. They're pretty much on top of each other. That's what I was looking for. I was looking for B, but I'm realizing that you're seeing something slightly different than you over there. This is the first time that has happened. Where I thought, they got everything right so far. Surely they can reach this graph. And we did. You were being really exact. Like it looks like the A is a little bit further than the C, and to you it looks like C is a little further ahead of A. I'm sorry about that. That's what happens on a curve. So you're being really good scientists because you're all like, let's make sure that I got this exactly right. Yes?
If they're the same wavelength, why is the energy output different?
Ah, okay. Because you can make stars bigger. Right? You can make the whole thing bigger at the same temperature. We'll get into that though. You're running ahead of schedule. But all right. So the point is, these stars, while having other properties be different, their central temperature, their main temperature is the same. Their peak wavelength, they peak roughly at the same point. Although it looks slightly different to you guys than it does to all over here. Okay. So, what happens, which one of these stars is then the biggest? If star A is over here, star C is over here, are they both the same? Or, I should change both to the same. That's not English, is it? We cannot tell from this graph. Which one is the biggest? Voting in 1, voting in 2, and voting in 3. And thanks to the question, we are now all in agreement that star A is the biggest star, right? So you can make a ball the same temperature, but much bigger, and we will put out what we're doing. Which one of these stars looks red? And so this is where I've got this little word soup down here, and I should explain that. R is the reddest filter, the reddest color that we can sort of observe, and V is the bluest one. You're going to go, why have you named them this way? Because those were the names of the little pieces of colored glass that we slid into our telescopes, and we've still stuck with these names now. So this is the blue side of what we observe, and that's the red side that we observe. So which one of these stars looks red? Does star A, both, star C, or neither? Voting in 1, 2, 3. Very nice. You're all peeking the blue. So there's more light coming off the blue. Which star peaks in the blue? Voting in 1, voting in 2. You got this one. Yes, excellent. All right. So a little in-class assignment. We've got our first concept down, right? Stars are big balls of gas. They have one temperature, and we know what their graph, the graph then looks like. And how are you all tuning up? So, just in case you weren't here the first class, I have a friend who studies how people study, which is a fun thing to have to do. And one of the things that happens is that nobody can pay attention after somebody's talking in front of the class after 30 minutes. And I would really like, this is the group work, right? So you have to collaborate with somebody next to you. I only grade the ones that have more than one name on them. All right? So 2 things. I was talking about this on Thursday, but I realized that that's now a week and a half ago. You have to collaborate on these. These are the in-class assignments. The only way, can we just press something? The only way to get credit on this is if you have more than one name on there. So you have to be in groups. It is mostly A. I'm checking if you got participation, like did everybody, or is your name on there? This is not a gimmick. I always manage to sort of run out of them by here. I don't know why. So I'm very good at handing out paper. So find a friend, make a friend, and work on this together. you're absolutely free to, keep a copy if you want, but we've got about 8 minutes to do this. This is the in-class participation component of the class. And then we can go back to thermal radiation. It's a little clearer on the sheet, isn't it, that A and C are the same. I'll walk around, happy to answer questions, and then at the end of the class, you can move up there. Okay, so we'll work with it. I'm just watching it and like I'm realizing this is our first campaign. It's all good. Yes. I would like one with all your y'all's group name on it. Make sure that your names are clear with your groups are mean more than one person. Is it relative to how much red light is? Is it working light, or is it the star angle? The star zero. So this is part of it. You have to work with a little bit of it's okay to go. It's down. But this is sort of help with the reasoning because this is the questions that Everybody have a last question? I'm going. So there's a break in the middle of every class where we work on a problem. Because I'd like you to work the idea. You come in, you've done the class assignments, you've got the concept, you've answered some questions, and then you come in, we talk about it, and then we work on it. All right, so there will be something like this for every other class. So sitting in the back and not interacting with everybody because it's a nice dark big room. It's not really, I'm sorry. All right. So we can get some intuition that once you get the coolest stars are about 1,000 Kelvin. Big broiler. All right, and we've found even cooler ones that are essentially a good temperature to bake cookies at. And then we end up with 10,000 Kelvin. Like you see the temperature, it goes from red to yellow to white to bluish light. There's even a few hotter than that. That's essentially a welding torch, right? If you see somebody arc welding, for example, have you seen somebody arc welding? Has anyone seen welding happen? Yeah, you see the whitish, can almost not look at it, bluish light that comes off it. We're talking this kind of temperature. And so, but if you want to know how much comes off a given amount of surface, so if you look at a piece of surface, like this is a piece of the sun, right? I have a little carpet here, or you just take a little chunk of the floor here. Here's a tiny, not everybody can see that. All right, a little panel like this, right? You take an area, and from that area, how much power is being radiated? It's essentially constant, but it goes times the temperature to the fourth. So you can imagine that this and that one, this one's putting out way more on the surface. So if you have a particular surface of the star, and it is a particular temperature, since it goes like to the fourth, so you have to multiply the temperature 4 times. But sorry, I'm checking here with you all. If you see this, do you know what happens to the temperature here? If I say the temperature squared, right, it's the temperature times the temperature. So it's the temperature to the fourth, it's the temperature times the temperature times the temperature times the temperature. So any increase in temperature skyrockets the amount of energy coming off the surface. So that's per unit area, right? So this panel, if it's a certain temperature and I heat the temperature up, increase the temperature, like more energy comes off. Once again, we're dealing with a constant, and because 2 people found it, we call it the state constant. So it's the amount of watts, so that's the amount of energy coming off per square meter, so per area, and then temperature to the -4, because basically I'm trying to get the temperature back up. Right? So that's the unit of this constant, and so if I multiply that times the temperature 4 times, I end up with how much watts per square meter is coming off. That's well and good, so I know how much energy any given chunk of a sun or a star radiates out. But what happens if I want to get the whole thing, right? How much energy is coming off this particular star, this energy, this black body? So if I want the total luminosity, if I want to know how much is coming off it, I have to multiply by the surface of the area of the sphere. So that is 4 pi times the radius of that star. So 4 pi, that's the constant, times the radius of the star, times another constant, times the temperature equality. So that gives me the total luminosity of the star. So I can make a star more luminous by either making it bigger, same temperature, just bigger bulb, or I can heat it up, right? I can increase that. So double the size would radiate energy 4 times faster, or if I just increase the temperature a little bit, it would go even faster. So it depends if I need to get rid of a certain amount of energy, because the center of the sun is really hot and constantly produces more energy, how do I get rid of it? I could either become bigger and have a bigger radiating surface, so a bigger radiator, or I can increase my temperature. So big and hot objects have great luminosity, and small and cool objects have lower luminosity. There's 2 ways to increase the luminosity, by temperature or by size. And we'll see that again when we start talking about stars, because basically there's a couple of classes of stars, and they're either the same temperature but massive, just really big in size, or they are the same temperature but tiny, and just as almost really and or less, but they're really, really hot. So, which one of these stars is hotter, star A or star D? Star A, star D, the same, we cannot tell from this graph. I'm really realizing just now, as I'm reading this for the 10th time, that I should put star D under D, because otherwise it's confusing. I keep doing this, I'm sorry. So, star A, star D, the same, we can tell ourselves from this graph. Plugging in 1, 2, 3. Which one of these is hotter? Majority A, okay, yes. Which is larger, star A or star D? 41, 42, 43. Okay, got a little bit of spread here. So, time to do my little round. Talk to each other, even if the two of you agree. You've got about 90 seconds to explain to you why you think your answer is right. All right, here we go.
I was thinking red,
Let's see how we do. 41, 2, be over there. Right. So let's reason it out, right? Star A is hotter. We're in agreement on that, right? Star D almost gives off the same amount of energy, like same peak, but it's at the lower, it's a lower temperature. So in order to be a lower temperature, yet get all the way up here, what does it need to do? It needs to be way bigger. So if you're a lower temperature and you still want to put out as much energy, you have to be giant. So that's a thing to remember. If you are at a lower temperature, still want to radiate as much away, you have to puff up, you have to get bigger. And funny enough, that's how stars behave. Some of them get bigger just to get rid of their energy. Okay, now, we're going to read the first astronomical diagram here. So far, this has been physics. Black bodies is straight up physics, it's experimental. For example, if you, a few years back, who has heard of the paint Venta Black? Right? If you paint something Venta Black, it radiates almost as a black body. It's amazing, right? So it's getting perfectly black, but also radiates as a black body. So this is a astronomer's diagram, and we'll get to that in a second. Because we're just reading is which star is hot and dim, right? So on the y-axis, we've got the luminosity in solar units. So thousands, hundreds, tens of thousands, thousands, hundreds, 10, 1, 10, 100,000, 10,000 solar units, and temperature goes from 5,000, 10,000, 20,000. It goes this way, and I'll explain to you in a second why. Which of the stars is both hot and dim? 1, 2, and 3. Yeah, it's the whole smorgasbord. It's ABCD. Right. You're kind of going like, why are you making me read graphs? Well, it's a science class. And even if you will never read an astronomy graph ever again, and I understand if you never want to, you will be presented information in graph form. And I want you to take that graph and examine it. So, for example, you look at this, and it took a minute because the temperature is going the wrong way. Wrong being a convention here, because we usually plot anything on the x-axis increasing from left to right, because that's how most of us read. Right? So that's a convention. However, sometimes conventions depend on the area that you're in. So funny enough, in astronomy, the convention, and I kid you not, and it's the pain of my existence, the convention for temperature plotting stellar temperatures is going up from right to left. So I want you to examine when you are being presented with data in a visual format. Hey, which way does the axis go? Where's the minimum? Where's the maximum? Where's like, why does it stop here at 1,000? I was like, that's right, there are no stars much lower than that. Why does it stop here at just a little over 20,000? Oh yeah, that's okay for stars, right? So this seems to be good range, and we'll get to it when we talk about stars, but there is a historical reason for that. So essentially, it's a convention within astronomy. And now we're stuck with it because somebody decided to do it this way 110 years ago. So now we're stuck. So this is worse. That's already 2,000 years old and nobody's changing it, right? So I will occasionally do this exactly so that you can read a graph. Which star is cool and dim? Let's see if we can find those. Plotting in 1, plotting in 2, and plotting in 3. Easy. Now you find your way around a color magnitude diagram, which is the important thing in astronomy, one of the important things in astronomy to understand stars. All right, so we have detectors, and in fact, you've been using your detectors almost for an hour now. And so they work between 380 and 749 meters. It's this one. But as far as a light gathering thing is concerned, this isn't particularly big, right? We have pretty good night vision for non-predatory species, but that's about it. We still stub our toes because we don't have a ton of light gathering ability with our eyes. And they also, it's always a fun thing, when do I wipe out against this thing? It also refreshes, like a video camera, for example. Although, again, video camera, giant thing, okay? You have a camera that has a frame rate, it refreshes. It also detects light in using 3 sets of cells in your retina, and so you've got S, M, and L cones, and those are sensitive to color, and then you've got the rods, which are only sensitive to light and dark. So if you're an astronomer in the middle of the night and you're trying to, look at Jupiter or something like that, you're not going to perceive a lot of color simply because your night vision is just light and dark. That is the color. So it also depends on how sensitive these things are, and there is not everybody's equally sensitive to them, and not everything. Some people are insensitive. And so the property is sort of a property of the observer. So how you perceive light is a little bit based on how your eyes work. For example, who here cannot see a number in this particular, I don't want to single you out, but there are a few people who cannot see a number here. I'm sorry, you might be colorblind. Right? That's the thing. This is how you get tested for if you're in the Air Force or you go for flight school. It has a little 74 here, but you have to be able to see the difference between red and green, which is very hard to do. And so we need another instrument in order to augment our eyes, at least initially for the optical light. And so we need a telescope. And the main thing is to gather more light. Magnifying is sort of a secondary thing. You think if you look at these very large telescopes, like, oh, they must be magnifying things. No, we need more light to be sensitive to the faint stuff, because a lot of the universe is quite faint. So you can have 2 kinds. You can either use a refracting telescope, that's how we got started, so basically binoculars, or the very first telescopes had lenses in the front, ground down to a shape, and then as a glass lens to concentrate more light into your eyes. A reflecting telescope basically does the same thing, but instead of a lens, they use a reflection in a mirror, because you can make bigger mirrors than you can make glass lenses. Again, I always have to stick in an HKCD at least once. So it is quite tricky to make a big, clean lens like that. Beyond the kind of sports you've seen maybe the sports photographers with their absolutely giant trumpets and then like a camera at the back. Like that's sort of the biggest you can get the lens. It takes they have to be long, they're sort of mounted on things. You actually have, the color doesn't go through the same way for red as for blue. And here so you can make it much more compact with a short focal length, so you can actually reflect it like that and actually use a much shorter telescope. So what's the big benefit of reflecting telescopes? No spherical aberration, weight, no vampires, well, they are shorter. What do you think is the big thing that is the difference? 1, 2, 3. Most of it is shorter. No spherical aberration is also a big thing. Somebody like Jupiter doesn't have a little halo around it. So both of the answers are right. I'm just curious who answers no vampire. That's a fun one. So you can have one where you have a lens here and a secondary lens. You have a really long tube. And if it's reflective, you sort of double up so you can have a much shorter tube. It either can go out the side or you actually have to sit at the top of the telescope. So that used to be a thing where you spent the night at the top of the telescope, or it reflects back into the little hole in the back of the mirror, and so you can see it there. Or even you do it 3 times, so you can stand at the bottom and have the eyepiece there. So there are 3 main functions: gather more light, that's actually the main one; decide or finer detail, resolution, that's the secondary one; magnify being the absolute last one. Really, if you can see fine detail, magnification is relevant to blow up picture. So Galileo's telescope is the first time that we sort of augmented our vision on the night sky. And so finally, we had the Mark-1 eyeball that actually worked okay for anything that's bright in the sky. But as soon as you just put a little bit extra, and this is not big, right, mind you, right? The actual gathering area is a little bigger than a silver dollar. So it's about that. It's not even a full. Trying to come up with like a household item that's about this size. It's sort of like a small glass in diameter. It's not terribly big. And so that's at the end here. Then he has because the focal length is really long. It's about as long as I'm tall, and that's what you a little shorter. And that's what he pointed depicted sort of here, where it's like it's kind of odd because you're definitely looking at the sea here. You're not looking at the night sky. But that's sort of what the first telescopes and binoculars look like. Right. So, but that had enough extra diameter to sort of see and emphasize faint details like the moons of Jupiter, the mountains on the moon, and the rings of Saturn. So refracting telescopes sort of became a race like who has the biggest one, but then you also have to have not only bigger diameter but also have a long tube at the end. So just to give you a sense of scale, that's a beach chair. And so, that's the observing chair. That's not a beach chair. It's not on the beach. But somebody who's sitting down here. Here's the whole floor moves up and down, and you really sit in the back like with your little eyepiece, looking at stars. And you can look a lot. You can learn a lot about stars that way because you're already improved it. This is at Yerkes Observatory. That's in Wisconsin, and it's just been restored as this magnificent dome. Reflecting, the nice thing is, suddenly this enormous long thing sort of halves in distance or more. Mirrors are easy to make optically perfect, and so you fold the light, it's easy to deal with. So Newton of gravity's fame already made a shorter version of this, and so this is sort of like Newton's telescope, and really almost all telescopes now use mirrors instead of lenses. So a lot of it, what you can see, is not just how good your eyeballs are. It is really like if you want to observe with a telescope, is how good is the telescope, size, engineering, really how well it's made. And so a lot of the early discoveries really depended on, for example, how well somebody could grind lenses. The other one is like what do you detect with? And if you had good sharp eyesight, that's great. But if you have good instruments at the back, then you can detect more. So often, as it happens, really old, like 100-year-old telescopes suddenly become cutting edge because we put a new instrument in the back. And you've seen this particular race of detectors already because your first phone did not have a camera that had as much detail as the one that you're carrying now. The phone that you have now could take pictures of your friends in the, while you're out on a walk in the dark, and while your first phone could definitely like have this washed out great picture. You've seen detectors improve over time, right? So this is fun because this sort of happened during your lifetime. I think this thing came out when you all were born, and so you've seen the generations improve over time. So we have the exact same thing. We just switch out the camera and suddenly we've got a new telescope. And it really is important where you put it. So if I put it down here, I'm taking pictures of the underbellies of UPS planes all the time, so it's really not a great location. However, if I put it on top of a mountain with nobody else nearby, hey, I've got clear skies and I've got no light pollution or anything. How well I can actually see detail depends on two things: the wavelength that I'm looking at. Now, that's always in the optical if it's just my little telescope, and the diameter of the telescope. I can see more detail. I can separate out more things if my diameter is bigger. So this is sort of the perfect resolution. So far, small is better. If I get this ratio down, I can see more detail. This is true for all wavelengths. So when we go to radio astronomy or ultraviolet astronomy, X-ray astronomy, depends on the diameter and the wavelength that I observe. So if I look at here. So if I do lambda over d and I have the same diameter, I'm seeing way more detail in the ultraviolet than if I had the same diameter and doing a radio. Because the radio wavelengths are so long, I have to actually be proportionally larger. Which is how, and I have a lot of slides on pictures of telescopes, but I can always do that later. Radio telescopes tend to be these enormous metal dishes. Right, so if you go to Western Virginia, there's a really big one, or in New Mexico, there's a whole swarm of them. You either need a whole field of them, or you need a really, really big one, or the radio astronomy any resolution. Sorry, I just wanted to show that part. Okay. Now the last part is our eye refreshers, and so you can put the nicest telescope, you put an eyepiece on it. Remember one of the astronauts saying, I really wish there was an option to put an eyepiece on Hubble, because that way I would have been the one person who's looked through the eyepiece of Hubble, but too bad. Eyepieces are great. It's wonderful to see it with your own eyes. Here's the problem, our eye refreshers. So after a not even a second, it's a fraction of a second, your eye basically resets and starts gathering light again. It resets and starts gathering light again. It has to, because you wants an updated picture of your environment. This is important. There could be predators about, or you could be hunting something, right? You need updated information. So you don't want to stare at something and basically increase the dimness. And so what you need is something that actually gathers light over a longer period of time. And that happened when we started with chemical photography. So that's the first thing that can actually gather light over serious amounts of time. And so you have some of these very first pictures of Andromeda with the telescope using this chemical photography. These days, I don't think anybody uses chemical photography anymore. Who has actually handed in a little roll of film to have it developed and come back? Oh, cool. There's a couple of people who actually enjoy photography. That's fantastic. All right, so that's a whole thing, right? To have black and white photography and have the film developed. It looks a little different than CCDs, but when we went to CCDs, it really is the same thing. Suddenly this thing is super sensitive. About 70% of the light gets detected versus film, which is only 2%. So you have to imagine that kind of difference, right? Suddenly you have to get the same picture, you have to look at it for hours versus this is 2-minute exposure, done. And so CCDs are so much better than that. And well, okay, we all have one of CCD cameras. Sometimes maybe you have like one of the nicer cameras. And of course, if you're in astronomy, we've got to have a really big camera in order to do that. Currently, the biggest camera in existence is going onto the Moon. Observatory, and those are, you know, just fields of these CCDs. Be sensitive to that. I have one request from you all. Who here hasn't done that pre-test of the pre-post test? I would ask you to do it for me, please. So I'll explain. I have y'all's pre-test here. This is sort of the first step in getting extra credit. I'll be very happy to do it. The main reason that I'm doing this test is the following. I'm trying to gauge how well I do with this class. The best way I can do that to compare to other professors is by doing the standardized test. And the best way I can get you all to do it is to say you'll get extra credit if you do both the pre and post test. So if you haven't done it, please come over here and take the LCSI test real quick. Yes?
If we like got partially done.
Oh, please. Yeah, please. I'll happily give you a new one if you can finish it. Do it properly.
We gave you our version.
I'll swap it out. Is that okay? Yeah. Yeah, that's great. So you don't have to do great at this. It's for me just to understand how well I do it, right? It's for me to understand how well I'm teaching you these concepts, how much is sticking. And for that, I need to know how much you came in. Because I've had people who used to be a physics professor in a past life, and they're like, yeah, they're doing great at this test. I wonder, but maybe I didn't teach them anything. So I want to know how well I do, and that's what this is a good one. So if you're doing this, otherwise I'll see you on Thursday, and we get the plan of this. So make sure you come in on Thursday. They'll be at the door. Please grab one of these, because we'll actually use this as our yes. Drop those off at the technical side. Yes. Hi. Yes. So this is my little, yes, what design has been, Just go down. Pre-post, pre-post, I want to figure out.